Let's talk about the acid-base definitions for Bronsted-Lowry and also Lewis. And we'll start with Bronsted-Lowry. So a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So let's really quickly review what this definition means by proton. So if I look at this diagram right here, I'm going to draw the hydrogen atom, or the most common isotope. So hydrogen has one proton in the nucleus and one electron somewhere around our nucleus, so negative charge like that. And so we would say this is hydrogen, right? And then we put its one valence electron right there to represent the hydrogen atom, or the most common isotope. If we were to somehow take away this electron, right, we would only be left with the proton here. We'd only be left in the proton in the nucleus. And so when we're talking about a proton, we're talking about the nucleus of a hydrogen atom, which is equal to H+. So no longer are we talking about the electron. So let's see how this applies to an acid-base reaction. And so we start over here with water. And then we have HCl over here on the right. Now, in this bond between the H and the Cl, right, one of those electrons came from the hydrogen and one of them came from the chlorine. So let me just go ahead and draw those in. So the one from the hydrogen, I'm going to put in blue here. And that's this hydrogen, that's this electron from hydrogen right here in blue. And then for chlorine, I'm going to make that electron green, so right in here like that. And so for this acid-base reaction, a lone pair of electrons in the oxygen is going to take this proton, right? So just the nucleus of the hydrogen atom, leaving the electron in blue behind. And that electron in blue stays behind and ends up on the chlorine. And so let's go ahead and draw what we would form from that. We would have oxygen here. The oxygen had two bonds to hydrogen, and the oxygen just picked up another bond to hydrogen. And so let me go ahead and mark those electrons. So these electrons in here in magenta, right, formed a new bond with that proton. So that's this bond right here. And then we had some electrons on oxygen. Let me go ahead and make those in red. So these electrons in red, right, on the oxygen didn't do anything. So they're still there. So they're right here. And that's going to give that oxygen a +1 formal charge. And so this is the hydronium ion, H3O+. Our other product, right, we would have our chlorine, which had 3 lone pairs of electrons around it already. And then it picked up both of those electrons. Let me go ahead and mark them. The one in green that it had originally brought to the dot structure, and also the one in blue, the one it took from hydrogen like that. So chlorine now has a negative charge, so it's really the chloride anion. So this would be Cl- like that. And so let's identify our Bronsted-Lowry acid and our Bronsted-Lowry base for this reaction. So let's go back over here and see what happened. Right, so the H2O, the water, right, acted as a proton acceptor. It accepted a proton from HCl. So water would be our Bronsted-Lowry base. And HCl donated a proton to water, so HCl would therefore be our Bronsted-Lowry acid. So let's go ahead and identify conjugate acid-base pairs here. So if HCl is our Bronsted-Lowry acid, right, I could think about its conjugate base over here would be the chloride anion. So this would be the conjugate base over here. So conjugate base. All right, so H2O, right, was our Bronsted-Lowry base, and then over here we can find its conjugate acid. That's H3O+. So this would be the conjugate acid over here. So when you're looking for conjugate acid-base pairs, you're looking for one proton difference. So H2O and H3O+ are a conjugate acid-base pair, and HCl and Cl- are a conjugate acid-base pair. And if we look at what we have on the right here, right, we're now saying H3O+ is an acid and Cl- is a base. And so one thing you'd think about is H3O+ donating a proton to Cl-. And so we'll draw a little tiny arrow going back to the left, because the equilibrium for this reaction lies far to the right. So you're going to get a lot more of your products on the right here. But just thinking about these definitions, right, H3O+ would be donating a proton and Cl- would be accepting a proton. The chloride anion would be accepting a proton. But again, we know HCl is a strong acid, so we know the equilibrium lies far to the right. So that's the idea about Bronsted-Lowry. Let's look at another definition, which is actually a little bit more broad. So this is Lewis acid and Lewis base. So a Lewis acid is an electron pair acceptor. And so an easy way to remember this is acid acceptor. and a Lewis base is an electron pair donor. And so one way to remember that this Lewis base is an electron pair donor is to, if you think about this B, right, being lowercase, right, and then just flipping it around, right, you would get a D here. So you would get a D. So base is a donor. So let's look at this reaction here, and we have this cyclic ether over here on the left, and then we have borane over here on the right. Now, notice there's no octet of electrons around boron, right? Boron's only surrounded by 6 electrons here, and that makes it very reactive. Boron is sp2 hybridized, which means it has an empty p orbital. And so let me go ahead and represent that empty p orbital like this. It's able to accept a pair of electrons. And the ether over here is going to donate a pair of electrons. And so let's go ahead and show what happens, right? The oxygen here is going to donate a pair of electrons into the empty orbital, right? And there's going to be a bond that forms between the oxygen and the boron. So the ether over here is donating a pair of electrons, so that must be our Lewis base. And borane over here is accepting a pair of electrons, so that's our Lewis acid. Let's go ahead and draw the product for our Lewis acid-base reaction here. So we have our oxygen is now bonded to the boron. The boron is still bonded to 3 hydrogens, so we draw those in there like that. And let's follow some of our electrons here before we finish drawing everything in. So these electrons in magenta, right, formed this bond between the oxygen and the boron. And then we also had some other electrons, right, on that oxygen. Let me go ahead and identify those. So these electrons right here in red are still on that oxygen, so they are right here on that oxygen. That oxygen, therefore, has a +1 formal charge, so +1 formal charge on oxygen. And boron gets a -1 formal charge now like that. And so that's one Lewis acid-base reaction here. Now, the Lewis acid-base definition is once again more inclusive than Bronsted-Lowry. If we actually go up here to the previous reaction, we can actually classify these using the definition for Lewis acid and Lewis base. And so let's look again at what's happening here. Right? So water is donating a pair of electrons. Right? Well, according to Lewis base, electron pair donor. So we could say that water, right? We could say this is a Lewis base. And HCl, right, is accepting a pair of electrons, right? So electron pair acceptor is Lewis acid, so we could call this a Lewis acid. So notice it doesn't matter what definition you use, right? If you use Bronsted-Lowry, this is your acid. If you use Lewis, this is your acid. Or if you use, or over here for base, right, this is your base according to Bronsted-Lowry. This is also a base according to Lewis. And Lewis acid and base also have particular importance in organic chemistry because you can talk about the term Lewis acid as being synonymous with electrophile. So you could say this is an electrophile, right? And then you could say a Lewis base is an electron pair donor. That's a nucleophile. And nucleophile, electrophile are extremely important concepts to understand when you're talking about organic chemistry.